Okay, let's continue the discussion. First, let's define the image set and the inverse image set. So, definition. Let x and y be sets, and f from x to y is a function. Then the image of a set E in the domain X under F is the set we denoted by F of E. The definition is a Y in Y such that Y is equal to Fx for some X in X. Okay, so you just collect all possible images from E, not X, E. You collect all possible images starting from set E and put them together. It's called the image of a set. The inverse image of a set E in Y under F is the set F inverse of E. F inverse of E, by definition, it is X in X, X in X, such that Fx is equal to Y for some Y in E. So the inverse image of a set E just means the subset of X, so that the images of the element inside X is mapped to this target E. Okay, so you cannot map it outside E. Then the pre-image will be denoted, the set of the pre-images will be denoted as the F inverse of E. So first of all, here we do not need one-to-one property. Remember, when we define the inverse function, we need one-to-one property, but the inverse image of a set does not require the one-to-one property. Okay? All right. Now let's see the basic property of this image of a set and the inverse image of the set. All right, so let's see what it is. Let X and Y be sets and F from X to Y. And if E alpha in the index set A is a collection of subsets of X, if we have a collection subset, then the image of the union is equal to the union of the image. Well, the image of the intersection now it changes. It's a subset of the intersection of the images. intersection of the images. Okay? So this is about the image of a set, especially for this second one. Second one is a special. We will see why it is this way. Okay, and second, if B and C are subsets of X, then f of C without B contains f of C without f of B. All right, f of C. This is again, it's not the equality. It's not the equality. We will see the example, which shows this is really a subset. Okay, this is first, second, third. If B and C are subsets of Y in the image part, then the inverse image, the inverse image of B without C is equal to the inverse image of C without inverse image of B. This is equality. This is equality. Okay, whatever. 4. In the book, this is of number 4. This is 3. It doesn't matter. So if E alpha is a collection of a subset of Y, then the inverse image of the union is equal to the union of the inverse image, and the inverse image of the intersection is equal to the intersection of the inverse image. They're both equality. Okay. Well, let's change the index. So this is number 3. This is number 4. Well, to follow the textbook. The last property. If E is a subset of the image of a total domain X, then F inverse image of E is equal to E. But if E is a subset of X, then F inverse of F of E contains E. Okay, so these are 5 properties of an image of a set, inverse image of set with union, intersection, and complement. Union, intersection, and complement. Okay. Okay, now let's prove it. If it's equality, we prove it. If it's inequality, first we prove the containment. If it's a containment, first we prove this statement, and then we give the example so that it's really a proper subset sometime. Proof. Let's see. The first one, the union, the image of the union is the union of the image. So let's prove. For any Y belong to F of E alpha, there is an X in the union of E alpha such that Y is Fx. And so x belongs to E alpha for some alpha. Hence, y belongs to f of E alpha, which is a union of the union of f of E alpha. So every element, this implies f of union of E alpha is a subset of a union of f E alpha. All right, so every element of y, it is a element in the union. The other way, for all y in the union of f of E alpha, then there exists alpha in A and x in E alpha such that y is equal to fx. Y is equal to fx. Okay, and x in E alpha, x belongs to the union of E alpha. So y belongs to f of union of E alpha. Okay, every y, it is an element in the image of the union. Thus, the union of E alpha, alpha belong to A, is a subset of f of union of E alpha. You see, this is one direction, this is two direction. Combine these two directions, it implies image of the union is a union of the image. Oops, it's bad. It's bad. It's bad. I don't know. I didn't check the focus. Sorry. This is the first page. It's horrible. It's a second page. My bad. Okay. Okay, so we proved the part one. This is part one. Oh no, it's just first part of the part one. We are going to prove the next. We show that f of the intersection of E alpha is a subset of intersection of f of E alpha. Okay, just one direction. So for all y in f of union intersection of E alpha, this means there exists an x in the intersection of E alpha with y equal to fx. X belongs to E alpha, so y belongs to f of E alpha for all alpha. For all alpha here. It's in the intersection, so it works for all alpha in A. Hence, y belongs to the intersection of f of E alpha. So from here, you get this, so we finish the proof. We finish this proof. Thus, the image of the intersection is a subset of the intersection of the image. All right, the intersection of the image. Okay, now let's see when it is a proper subset. So for example, if f is from R to R, f is from R to R, E1 is 1, E2 is -1, fx is x squared, then intersection E1 and E2 is empty. So F maps empty set to empty set, but F of E1 is set singleton 1. F of E2 is a singleton 1 also. So the intersection of FE1 intersect FE2 is 1. So here's an empty set, here's a 1. So that's a proper subset. Okay? It's really a proper subset. The reason is that, check here, if you want to prove the other way, so for example, for all y in the intersection of Fe alpha, it means for all alpha in A, there exists an x alpha in E alpha with y equal to fx alpha. The problem is you have no any reason to claim that this x alpha is uniform. So for different alpha you will have, but here x alpha 1 may not be x alpha 2, though for different indices. So that's why you cannot go back and claim there is an x in the intersection. Okay, like this. So this one, this one has a preimage 1, and it also has preimage -1. Those two numbers are different. Okay, so that's the first one. We finished the first one, and with the example and with the argument why it cannot be the equality. And second part, we are going to show C without B is a subset of FC, FB. Okay, we want to show this. So for all y in FC, but without FB. So y in FC, this implies there exists a x in C such that y is equal to fx. But this y is not in FB. This implies for all t in B, ft is not equal to y. For all t in B, ft is not equal to y. But x is equal to y, so x is not in B. If x is in B, then fx is not equal to y. X is in C, but x is not in B. X belongs to C without B. Hence, y belongs to f of C without B. So we do have, hence, we have FC without FB is a subset of FC in B. All right, and again, let's see the example when you have a proper subset. The example is still this one. So this time we still choose F from R to R. C we choose 1, -1, and B we just choose 1. Then fx is x squared. Then FC without FB, you will see that F maps C to the singleton 1. It maps B also to 1. So with this the subtraction is empty set. And FC without B, you only remove 1, you still have -1. F maps -1 to 1. So this is a proper subset. These two things are not equal. All right, so it's the proof for the second part. The proof for the second part. Now let's see the proof of the third part. The third part, this is the third part. For the inverse image of a set, it's for the union intersection, they're both equality. Okay, so again, the union is not difficult. For all x in F inverse of union E alpha, this means fx belong to the union of E alpha. Fx belong to the union of E alpha, then there exists alpha in the index set with y in E alpha. No, I don't need it. There is an index set with fx belong to the E alpha. Yeah, fx belong to E alpha. So x belong to F inverse of E alpha. It is a subset of a union of F inverse of E alpha. All right, so every x here, it is an element in this union. We get F inverse of a union E alpha is a subset of a union of F inverse of E alpha. It's one property. One direction. One direction. All right. And the other direction. The other direction for all x in the union of F inverse of E alpha. Okay, then there exists alpha in A with x belong to the F inverse of E alpha. This is equivalent to say fx belong to the E alpha. Okay, fx belong to E alpha. Fx belong to E alpha. E alpha belong to the union, is a subset of union of E alpha. So fx is inside the union of E alpha. So this is equivalent to x is an element in the inverse image of union of E alpha. Right? So from here, you get x as an element in the F inverse of union of E alpha. So we get F union F inverse of E alpha is a subset of F inverse union E alpha. So this one direction and the other one direction. Combine them together, union F inverse of E alpha is equal to F inverse of a union of E alpha. Right? So that's the proof for the union. The union is not a problem because I don't care if they are uniform or not. It's just one enough. For the intersection. Okay, this is one part. For now, let's talk about the intersection. X is an element in the inverse image of intersection. So this implies fx is an element in the intersection of E alpha. So it implies fx belong to E alpha for all alpha in A. For all alpha in A, what does it mean? It means x belong to F inverse of E alpha for all alpha in A. Then x belong to intersection F inverse of E alpha. Right? So here, this is the definition of the inverse image. It's equivalent from here to here and here, the same thing. And this fx belong to the intersection, then fx belong to every set E alpha. And every set E alpha, this is if and only if. Then x belong to F inverse of E alpha for all alpha. Then x belong to the intersection. So you see here, actually we already proved the equivalence. Every step you have the equivalent result. Okay, every step have equivalent result. So that is the proof. We finished the proof of the second part of the part 3. All right, finish this proof. Part 4. Part 4, we're going to show that F inverse of C without B is equal to F inverse of C without F inverse of B. F inverse of C without F inverse of B. Okay. Still, directions. So for all x belong to F inverse of C without B, this is equivalent to fx belong to C but not inside B. Right? And this is equivalent to fx belongs to C and fx does not belong to B. And this is equivalent to x belong to F inverse of C, x does not belong to F inverse of B. Right? See, and this is equivalent to x belong to F inverse of C without F inverse of B. Again, you see this is a if and only if case. It's an if and only if case. All right, so we finished the part 4. Part 4, you don't need the 2 directions. Every step is 2 directions. And part 5, if E is a subset of the image of fx, then F inverse of f of F inverse of E is equal to E. We can cancel F inverse, but if E is a subset of X, not the image, then F inverse of F of E contains E. Okay, now let's prove it. For the first one, we want to show this. How do we show it? We prove 2 parts are same. So for all y in F of F inverse of E, all y in it, then it means there exists X in f inverse of E with fx is equal to y. Fx is equal to y. And this is exactly the definition of x belong to f inverse of E. Right? This is exactly the definition of fx is f inverse of E. The thing is that we have to claim y is inside E. If y, but how do you know it's y is inside E, right? So x belong to f inverse of E. This is equivalent to fx belong to E. And fx is a y, so y belong to E. Right? You see how I get it? So for every y in this f of f inverse of E, first of all, by definition, it means you can find the element x in this set so that fx is equal to y. X in this set, it means fx will be inside E. And fx is a y, so y is in E. So we get f inverse of E is a subset of E. The other direction, for all y in E, what does it mean? E is in the where E, yeah, E is in the f of x. So there exists x in x with y, no. Yeah, let's put x here. It's in the image set, so there exists x in the set x such that y is fx. Y is fx. So what we get, this implies, this is equivalent to x belongs to f inverse of E. X belongs to f inverse of E. Right? So y in E, y is fx. So x is a inverse image. F is inverse image. X is in the inverse image, then y equal to fx. It belongs to f. This is f. X belongs to the inverse image, f inverse E. Okay, so this is like a tongue twister. It's not difficult, but just a little bit twisting. So here, this f you copy it. X belongs to the f inverse of E. So that's why you have the belonging condition. So you get y is an element in the f of f inverse of E. So every E, it's a subset of f inverse of E. So you get two directions. So you get f inverse of E is equal to E. All right? Yeah. The other one, we only prove one direction and give example about the proper set. Okay? So for all x in E, for all x in E, x is subset of x, so we put a little x here. For all x in E, what we get, then fx belongs to what? Belongs to fe. Fx belongs to fe. Let's what do we get? Yes, fx belongs to fe. Then by definition, you consider this as a set. Fx is in the set. This implies x belongs to an inverse image of the set. inverse image of the set. So every E, it is every set E, the element belong to the F inverse of F of E. So E is a subset of F inverse of F of E. That's it. We only need one direction. How do we get the proper inclusion? So again, we choose a square function. E, we choose it as 1. Then fx, we choose x squared. Then f of E is a subset 1. And F inverse of F of E becomes a subset 1 and minus 1. You add some additional solutions, and it properly contains the original E, right? So we prove this the property. So when we have inverse image, the inverse image of a set and the image of a set, just be careful about this situation. Of course, if F is, all the problems come from the property that F is not a one-to-one. Here, F is not a one-to-one. See, we repeatedly use this example because this example is not a one-to-one example. If F is a one-to-one, then all the inclusions are identities. There's no less subset, proper subset. If F is one-to-one, then all relations are equalities. All the relations are equality. There's no weird proper subset. Okay, so let's see what exercise you can practice. Okay, so you can try the exercise. Page 33. You can try the exercise 6, 9, 6, 9, another 10. Yeah. Actually, you can also check the 11. If you feel it's too difficult, you can skip it. But it's a very interesting concept and important. It's called the algebraic number. Okay, so if the number is not algebraic, it's called the transcendental. So those two types of numbers are very important. So algebraic number contains all the rational numbers. Algebraic, and it is more than a rational number. It's larger, properly larger than the rational number, but it's strictly smaller than the set of real numbers. So this is a very good problem, and it contains the concept. If you don't have time or you have problem, you can skip the 11, but 6, 9, 10 are simple. It's not difficult. Okay? Okay, now let's move to the chapter 2. Chapter 2, we talk about the sequences in R. Sequences in R. So first, sequence. The most important thing is the limits. Limits of sequences. Okay, sequence is really by definition, by English, it just means a bunch of numbers. They're orders. So for the sequences, it has orders. Okay, and for the sequence, you can repeat, for example, 1, 1, 1, 1, 1 forever. It's also a sequence. Okay. So 2.1, the first definition. Let's define what the convergence is and what is the limit. So a sequence of real numbers xn is said to converge to a real number A in R. A sequence converges to a real number A in R if and only if for every epsilon greater than 0 there is in capital N in the set of natural numbers in general depending on epsilon. Okay, it depends. For epsilon is bigger, maybe your n is smaller. When epsilon is smaller, n is bigger, such that for all n greater than or equal to n, this integer n, the ops value of the difference xn minus a is going to be less than epsilon. Okay. So this is the epsilon capital N language about the definition of a limit of a sequence, sequential limit. Okay. So this is a complete definition. The definition stops here. And then we will have several phrases or notations to describe the same idea. In the book it says interchangeably. Okay. So first we will say the sequence xn converges to A. That's the convergence. Or we just ignore this. We only put ignore the sequence idea. We just say xn converges to A. When you see this, it still means the limit, the sequence converges to A. Or we will write the limit of xn n approaches infinity is equal to A. Or we write xn approaches A as n approaches infinity. Or we verbally rewrite the condition C. Condition C just says the limit of xn exists and equals just a verbal description of a condition C. So in the book it gave a very good description. So we consider xn as a sequence of approximation approximations to A. Approximation, their error. How do we control the error? Epsilon is as an upper bound for the error of this approximation. Okay, so when n is greater than this selected capital N, this condition, it means x minus a, it will be this inequality is equivalent to this sequence of inequality, combination of inequality. So this is error bounds. When this index is sufficiently large, it becomes upper bound about the error. Okay. And keep a general idea in mind. N will approach infinity. This index N will approach infinity as epsilon approaches 0. When epsilon approaches 0, smaller and smaller and smaller, this N will become bigger and bigger and bigger. So it means if you have a very, very small bound for the error, then you have to choose your xn sufficiently close to A. Okay? Okay. Let's just do one example. Basic example. Prove that limit 1 over n, the sequence is 1 over n, is equal to 0 as n approaches infinity. Okay, so proof. Let epsilon greater than 0 be given by Archimedean principle. Archimedean principle. Whenever you have Archimedean principle, you compare two numbers. This time we compare 1 with 1 over epsilon. This is B, this is A. There is a capital N in N such that 1 over epsilon is less than N. B less than N times A. B less than N times A, right? Okay. And they are both positive. When you take the reciprocal, it's equivalent to 1 over n is less than epsilon. Okay, 1 over n is less than epsilon. Then for any n greater than or equal to capital N, 1 over n is going to be less than 1 over capital N less than epsilon. Well, if you want, this inequality can be written as the ops value of the difference. So for any epsilon, there is a capital N such that for all n greater than or equal to capital N, absolute value 1 over n minus 0 is less than epsilon. And that's exactly the definition of a limit of a sequence. So by the definition, of the convergence or the limit of a sequence, the limit 1 over n approaching infinity is equal to 0. Alright? It's equal to 0. And we say the condition in the definition is satisfied, then this sequence has a limit. Of course, we never say all the sequences have a limit. So now let's see the example so that it has no limit. The jumping sequence. This one has no limit. Has no limit. Okay, so let's try it. Whenever you want to show it has no limit, either you already have sufficient information or you have to use the proof by contradiction. Assume that the limit of -1 to power n approaches infinity is equal to a some number. Then by definition, we will have, by the definition for any epsilon greater than 0, there is and capital N inside the set of natural numbers such that this quantity -1 to nth power minus a up's value is less than epsilon. All right, so choose. So here, let's choose epsilon, very small. So let's choose 1/2. Choose epsilon to be 1/2. For n odd, the -1 to nth power is equal to -1. And n plus 1 becomes even, is even. N plus 1 is even, then -1 to power n plus 1 is equal to +1, right? So you have an odd and even element adjacent. Then let's check the -1 to power n minus the -1 to power n plus 1. The nth term minus n plus 1's term. It is equal to -1 to n minus a minus -1 to n plus 1 minus a. So far it's equality. Then you apply the triangle inequality, you get this. And when n is sufficiently large, for n greater than or equal to capital N, n greater than or equal to capital N. Well, odd even number, they exist all the time. It doesn't matter which interval you choose. So this difference is less than epsilon. This is less than epsilon. Epsilon is 1/2, so it's less than 1. Right? This is 1/2. This is 1/2, so it's less than 1. But the thing is that this place we get a -1 minus minus 1. -1 minus 1 is equal to 2. So we have 2 less than 1 contradiction. This contradiction comes from the assumption the limit exists. Hence, -1 to power n has no limit. -1 to power n has no limit. All right, so let's approve. Okay, so that's just the beginning of the chapter 2. We will have more examples of properties in the next short video. Okay, we'll stop here.